Hello and welcome to part 1 of module 20 in our C language series. This module is going to focus on C in the context of artificial intelligence. And as we all know, artificial intelligence or AI is mainly focused on finding solutions to problems. Now we could classify problems into two types. One type that can be solved using a predeterministic procedure that is guaranteed to succeed. And we could take this procedure and translate it to an algorithm for the computer to execute. This type of problem is known as a computational problem. The other type of problem is, of course, a real world problem. And as you will agree, real world problems can rarely be solved using a computation. And that's mainly because real world problems are characterized by their complexity and their magnitude. And so we need to search for solutions to these problems because what we perceive as a solution may not actually work. This is the type of problem solving that AI is primarily concerned with. Now, it has always been the dream of AI to develop a general problem solver, one program that can solve many different problems without the computer having any prior built-in knowledge specific to these problems. But this again is a dream difficult to realize. One of the main ingredients, though, of a good problem solver is a good search technique, and this is what our module is going to focus on. Because remember, searching is central to problem solving, and problem solving is a critical ingredient of intelligence. Now let's look at how we can represent real-world problems. Let's take a common problem. We've lost our keys. This is our home space. We're standing at this point. One of the routes we could take to look for our keys would be something like this. We go through the hallway into bedroom 1. We don't find the keys there, so we come out of bedroom 1, back to the hallway, and we go into bedroom 2. We don't find the keys there either, so we come out of bedroom 2, back to the hallway, to the master bedroom. We don't find the keys here either, so we go back to the hallway, to the living room, finally to the kitchen where we find the keys. Now we could represent this entire home space, the search space, if you will, as well as the route we took to find the keys using a tree. But before we do that, let's familiarize ourselves with the terminology. Now we've all heard the term node when we talked about binary trees. The node in the context of the home space would be a room. So every room, in essence, is a node. The terminal node could be the bath or the bedrooms, essentially because they are dead ends leading nowhere. The search space, as I said earlier, would be the entire home space. The goal in this case would be the kitchen. Now we talk about heuristics. What exactly is the meaning of this term? Heuristics refers to the cognitive or thinking methods that we as human beings use in order to take a quicker decision or to arrive at a solution faster. Right now, we haven't really used heuristics in our example on the keys, but we will talk about heuristics in detail in a later session. The solution part is, of course, the route we took to find the keys. Now that we're familiar with the terminology, let's go and put this all into a tree. So this is our home space. As you can see, every room is a node, and the terminal nodes are the bedrooms and the bath. The kitchen is the goal in this case, and a solution path would be something like this. We start at the living room, go through the hall into bedroom 1, then out of bedroom 1, back to the hall, into bedroom 2, out of bedroom 2, back to the hall, then into the master bedroom, and out of the master bedroom back to the hall, and then to the living room, and finally to the kitchen where we find the keys. Now that we've seen how we can represent a real-world problem, let's talk about a branch of mathematics that is widely used in the field of artificial intelligence, and that is combinatorics. Take a problem like this one. Without combinatorics, we would lay down the different combinations, arriving at 6 unique combinations. But of course, we could do this in a better manner using a function from combinatorics which we're all familiar with, and that is the factorial. So for 3 objects, 3 factorial would give us the maximum number of combinations possible. For 5 objects, 5 factorial would give us the maximum number of combinations. For 10 objects, 10 factorial would give us the maximum number of unique combinations. I hope you get the idea. But what if we had 1,000 objects? Then the number of possible combinations is a really large one, which leads to what is called a combinatoric explosion, which means that the number of possibilities or the number of possible combinations is so large that it is impossible to examine each of these combinations or each of these possibilities separately. Put this in the context of nodes and trees or nodes and search space. For every additional node added to the search space, the number of possible solutions is going to be far greater than 1, right? Which leads us to the discussion on the exhaustive search. And this technique means that we need to examine all nodes or all possible solutions, right? Now, while this will give us the best solution because it always works, is it really practical? If we think about it in terms of computer space and time, this particular search technique is going to be using a lot of computer time as well as computing resources, and therefore can be used only when we have a small number of possible solutions, which led the researchers then to develop newer and more efficient search techniques, which are the depth-first search technique, the breadth-first search technique, the hill climbing technique, and the least cost technique. Now, it's important to mention here that both hill climbing and least cost are built on the basis of the depth-first search technique. We will be discussing the depth-first search technique today in detail. We'll write some code on it as well. But before we do that, we need to understand how to evaluate a search. And there are 2 factors to consider. One, how quickly a solution is found. And this refers, of course, to speed. And when we're talking about speed, there are 2 factors to consider. One, the length of the solution path, that is the route to the goal or the solution. And the other is the number of nodes that need to be traversed in order to reach that goal or the solution, right? There is a third important point to consider, and that is if we reach a terminal node and we haven't found a solution. Remember, a terminal node is also referred to as a dead end. So if we reach a dead end and we haven't found a solution, then we will need to go back 1 node and find a different path. This is what is known as backtracking, and backtracking from dead ends implies a wasted effort. And therefore, our search solution needs to be one that seldom or never backtracks. The next important factor to consider while evaluating a search is how good the solution is. And when we talk about good, we need to evaluate optimal versus good. Remember, the optimal solution can only be found using the exhaustive search. But as we saw, it's impractical to use an exhaustive search if the number of possible solutions is a large one, right? And so we would go with the good search solution. A good search solution is one that works well within a set of constraints. And the idea of the good search solution is once we found that solution, we're not going to go looking for the optimal search solution, right? Because we found a solution that works well given the constraints that we have to work with. Now let's look at a case study. We have a customer who wants to book a flight from New York to Los Angeles with a certain airline. The travel agent tries to convince the customer to choose another airline or select another airline because this one does not have a direct flight, but the customer is adamant. So what is the travel agent going to do? The travel agent will pull up all the scheduled flights for this airline and then try to figure out the routes that the customer can take to reach his or her destination. One of those would be New York to Chicago, then Chicago to Denver, Denver to Los Angeles. Another could be New York to Chicago, Chicago to Denver, Denver to Houston, Houston to Los Angeles. A third could be New York to Toronto and then Toronto to Los Angeles. Our task is to write a C program to do this in a better manner. So before we get down to writing the code, the first thing we'll do is put all this flight information into a tree. This is our origin, right? And we have direct flights from New York to these destinations. And then, of course, we have the via routes to different places, including Los Angeles. Right? Now, once we've done that, we can clearly see the routes that the customer can take, right, to reach their destination. Now, let's look at this in terms of the depth first search. So what the depth first search will do is it will explore each possible path to the goal, to the destination in this case, before another path is tried. Remember that once it's found a solution, it's not going to go looking for another solution. So if we put the depth first search in terms of a tree now, with our starting point being A, for example, and our destination being F, then the path to F could be something like this, where we start at A, we go to B, B to D, back to B, then to E and back to B, and then to A, to C, to F. Right? So in effect, this is the path AB, DB, EB, ACF. Now, if you look closely, what we've done is we've actually done an in-order tree traversal, right? Starting at the root, going down the left subtree, and then the right subtree, right? Now that we've done that, let's put this in terms of a procedure. So we would go left until a terminal node is reached or until the goal is found or the destination in this case. If a terminal node is reached, then of course we need to backtrack and then go right and left until we find a goal or another terminal node. And so we repeat this process until of course we find a solution or we reach the goal, right? Now let's look at what the program will need. So the first thing we'll need is a database, but of course we're going to substitute an array in our program. We need a function to place all the flight information for this airline in the database, in our case the array. We need another function to determine if there is a flight between two cities, and a third function to search the database, in our case the array, for a connection. Right? Now how do we control backtracking? So what we're going to do is we're going to use recursion and what is known as a backtrack stack, which is nothing but a stack. What will be the process? Well, as a node is encountered, it will be pushed onto the stack. And if we reach a terminal node, then we back up one node, pop that node off the stack, and then proceed to find another route or another path to the destination. The stack itself will be managed by two functions, push and pop. Push to place a node onto the stack and pop to remove a node from the stack. Right? So armed with all this information now, let's go and write a program using the depth first search technique to book a flight for the customer. Origin is New York, destination is Los Angeles. So now let's go to code blocks and we can start a new project. Click File and then New and Project. And then of course Console Application. Click Next. Click on C, Next. Give your project a name. And then click Next again. Finish. Right, so now we have got main.c, but of course we need another file. So click on File, then New, and then File again. C++ source, click Next, leave that as is. Click on the ellipses and put in the name of the file. I'm just going to call that rest of functions or FNS. These two need to be ticked, so click all. That will happen and click finish, and that's done. We start with main.c. If you double click on that, and then of course we don't need this particular line, so we can just get rid of that. We need to include string.h, and we need a directive #define that's going to be max of 100. So there's going to be 100 elements in our array, right? Maximum. Okay. We need to define our structure. So struct, let's say FLT information. So flight info essentially. And these will be the members. That will be char from of 20 bytes, and then char2 of 20 bytes, and then int distance. The last member will be a char type. Let's call that skip over, right? And this is essentially to prevent the same connection being looked at again and again. Okay, so this will initially have the value 0 when we load this array or initialize the array, and then later on, once we've checked a particular route, then we'll change that to 1, as in the value of skip over, right? Now we have another structure, struct stack, right, which will manage backtracking, and this will have again char from 20 and char2 of 20 bytes and dist, or rather int distance, right? Now we have certain functions, void root. We'll define this function in the other file, but we'll be calling it from here. So that's char start2, which is the parameter going there. And we have another function, is there a flight? So is flight, right? And that's going to have parameters char star from and char start2. Okay. And then we have another function to load the array. So we'll call that load array. No parameters to load array. And we have another function which will be called from load array, where we are adding each route that the airline runs. So add flight char star from, char start2, and int distance. Okay. Now we need to define our structure variables. So that's struct FLT info or flight info, and that will be flight array, and that will have max 100. So we can just put in max there as we've defined it here. All right. And the other structure variable will be struct, that will be stack, right? And this will be called backtrack stack or BT stack. And again, that will have max number of elements. Okay. Now that we have those two more variables that we need, integer type fpos equal to 0, and this will increment every time we add a route to the array or add that flight information to the array. and then int top of stack equal to 0. Right? I hope you're clear so far. Now we can write our main function. So in main, we need char type from, this is for user input, and 2 again for user input, both of 20 bytes. And we'll call load array. Once the array is filled with the route information or the flight information for the airline, we can ask the user for input. So printf flying from, and then of course we use a scanf, and the scanf will accept input until an enter key is pressed. Right? Comma from flush stdin, and another printf flying to. Right? And again, you can copy that scanf and change this to 2. Right? flush stdin. Once we have the input, right, then we can call isFlight. So isFlight, and we send in from and to. And then we call route. Now what is route going to do? So route essentially is going to be the function that is going to take the solution from the stack. This program will have the solution on the stack. So route, the function, will take the solution from the stack and give us the result. I mean the solution, that is. Right? So this now ends the main function. Right, now we can write the code for load array. No parameters there. And here what we're going to do is we're going to call add flight 11 times, right? Because those are the routes we have currently for the airline. So add flight, and we'll send in first New York being the origin. Destination is Chicago, right? And that's 1000 for the distance. Similarly, add flight, and next we will have Chicago as the origin, Denver as a destination, and of course put in the distance as well. Right? And similarly for all other routes. So that completes the code for load array. Now let's write the code for the next one, which is add flight. Remember, this is being called from this function, and parameters are char star from, char star to, and int distance or dist. And within this function, we'll check if fpos is less than max, which means we have space in the database or the array. Then we'll use memcpy and copy to flight ar, right, of index will be fpos dot from, comma, from, right? So this is our destination, from is a source, number of characters is strlen of from plus 1, right? Similarly, memcpy flight ar, index is again fpos dot to is the destination, 2 is a source, and strlen of 2 plus 1 is the number of characters, right? And then flight air of f pos dot distance is equal to dist, right? And flight air of f pos dot skip, we'll initialize that to 0, as I said earlier, right? Now f pos needs to increment by 1, right? Because we are adding, you can say, one element to the array, which is essentially the root, right? So for every root that is added, this will increase by 1. Now, if there's no space, as in if f pos is not less than max, then, so we have an else here, and we just printf flight database full. Okay. So that completes the code for add flight, right? The next function that we need to write will be in this file. So essentially main.c, we are done with the functions, right? So let's go now to rest of fns.c, and we need to copy certain things from here. So you can copy from #include stdio.h right up until the structure, right? Let's copy that into this file. Once we have the structures, now we'll put in our functions. So we have void root, and that's char start 2, which is the parameter. And then we have push and pop to manage the stack. So push is going to take char star from, and then char start 2, and in distance. Similarly, pop is going to take char star from, char star 2, and int distance. Okay. Then we have another function, which is find a direct flight. So void find direct, and just call it that. And that's going to take char star from and char star 2 as parameters. And we have one more function that is going to be finding a connection or a connecting flight if there is no direct flight. So find connect, and this is going to take char star from and char star to anywhere. So essentially what this function is going to do, which is flight, right, which is going to of course take char star from and char star 2 as parameters, is going to first call find direct, right? Oh, by the way, find direct should return an integer, not a void, because we need to use that integer, right? So both these will return an integer. So when isFlight calls find direct, it's going to essentially return the distance if it finds a direct flight. If it doesn't find a direct flight, it's going to return 0, in which case find connection will be called. So essentially we look for routes from the origin to anywhere, and then using recursion, we will then use anywhere as the origin or to anywhere as the origin and look for flights to the destination, right? So that's how we will find the route for the customer. Now we need to define a structure variable. So struct flight info, right? And that will be flight air of max and struct stack, right? And this will be bt stack, as in backtrack stack of again max. And these were the same as defined in main.c, right? Okay. Now we need to use the extern storage specifier, extern int EOS, as in top of stack, and extern int fpos, right? So we can refer to the same variables as in those which are global in main.c. Okay, we can start writing the code for the functions. So first we write the code for isFlight. Okay, so void isFlight, and that's going to bring in char star from and char star to. Within this function, we'll have in D, which will catch the return value of the find direct function, and dist, which will catch the return value of the find connect function. Okay. Then we have char, let's call that anywhere of 20, which will be used to call find connect, right? We send that as argument. Now we check if D equal to find direct, right? And find direct, of course, needs its arguments. That will be from and to. So if D equal to find direct from, comma, to, which means we have a non-zero value there in terms of the distance, then this printf is just for our reference, printf, and we will push this root onto the stack, from where the root function will pick it up and display it, because a direct flight exists, right? Now, if this is not a non-zero value, then what we do is we check if, and here we use dist to catch the return value of find connect, and that's going to take from and anywhere as arguments. And if that's a non-zero value, then we'll have a printf statement first, just for our reference, printf backslash n, comma, from, comma, anywhere, comma, dist. Okay, that's just for our reference. Again, once you've understood the code, you can remove this printf statement. Then we push this root onto the stack. So push, right, and from, to, and distance. Okay, then using recursion, we call isFlight again from within itself, passing in anywhere now as the origin and to as the destination. Right, so you see how this is going to be doing that depth first search technique, right? Now, if both these conditions are not met, so else, now we'll need to backtrack. So if TOS, that's top of stack, is greater than 0, which means there is something on the stack to pop, then we'll call the pop function sending from, to, and ampersand distance. And then we call isFlight again. There should be an underscore there, right? So isFlight again. We call isFlight again, that is sending in from and to, right? Let's check how we define this here. Oh, this should be an underscore as well, right? Because that's the way we've defined it in the main function, right? Okay, coming back to rest of fn's. Okay, so I hope you got this. This essentially ends the code for aceflight. Now we write the code for the function that is checking for a direct flight, which is find direct. And find direct is taking parameters char star from and char star to. Within this function, we'll have register integer type x, and then we have a for loop for x equal to f pos -1. Why -1? Because remember, when we added the last root to the array, fpos would have incremented by 1. Right? Essentially going to a blank space in the array. So we're just bringing it back to the last root that we added. Okay, so for x equal to fpos -1, as long as f is greater than -1, so that we get access to the first element, which is the 0th element, f minus minus. And within this for loop, we check if, and now we're using strcmp. We know strcmp returns a 0 if we found a match. So if not strcmp of flight pair, right, of x dot from, comma, from, and we need to check for the destination as well, right? So not strcmp again, flight air of x dot 2, comma 2. Okay, so if we found that match, then what we'll do is we will return the distance. So flight air of x dot distance. Pretty simple, this one. Yes. If we don't find a direct flight, we return a 0. Remember, this return value will be caught in this function, right? In D essentially. Okay, this completes the code for find direct. Now let's write the code for find a connection, right? So again, that returns an integer, int find connect, and the parameters are char star from and char star to anywhere, right? And within this function, we have int find pos equal to 0, and we have while, it's a while loop, while find pos is less than fpos. Right, so we're going through the array essentially. Within this while loop, we check if, again using string compare strcmp. So if not strcmp of flight air, and index will be the stem, find pos, right, dot from, comma, from. And there's another condition, and that one is not flight air of find pos, again being the index, or at, you can say at find pos dot skip. So if this contains a 0, right, which means this route hasn't been looked at earlier, then we'll use mem cpy and copy to anywhere, or rather to anywhere, right, comma, flight air of find pos or at find pos dot to. Okay, we're copying the destination. Number of characters is strlen of flight air, again at find pos or of find pos, right, dot 2 plus 1, right, and then flight air of or at find pos dot skip will now be set to 1 to indicate we've looked at this route already. And then return flight air of or at find pos dot distance, and that of course will be caught in the variable dist in isFlight. Okay, I hope that's clear. Now before we go back into this loop, we need to increment find pos. So find pos plus plus, right? If, for example, we go through the entire array and we don't find any connecting flight, then we just return a 0. Okay. Right, so that completes the code for the find connect function. The next function we write code for is the route function. So that's void route, and that's going to bring in parameter char start 2. Within this function, we have int dist comma x, 2 integer type variables. Dist is initialized to 0, as also x initialized to 0. We have a while loop while x is less than top of stack. So remember, this is the function that is going to give you the solution. We'll add up the distances. Dist plus equal to bt stack of x dot dist, right, to calculate the total distance or the route. And then of course we've got to increment x before we go into the while loop again, right? And then outside here we'll printf %s \n comma 2 and printf the distance. Printf distance is %d \n comma dist. Okay, and that completes the code for the route function. So now we've written the code for route, find connect, find direct, and isFlight. Now we've got to write the code for push and pop. So we start with push. So that's void push, and that's going to bring in char star from, char star to, and int dist distance. Within this function, we check if TOS is less than max, which means we still have space on the stack. Then we use mem cpy, and the destination will be bt stack of TOS, that's the index, dot from, right? So that's our destination. Source is from, and number of characters is strlen of from plus 1, right? And again mem cpy, and the destination will be bt stack of TOS dot 2, comma, 2 will be the source, number of characters is strlen of 2 plus 1, right? And then BT stack of TOS or at TOS dot dist equal to dist, right? And of course TOS plus plus to say we've added one more root to the stack, right? Now if this condition is not met, then we'll just print stack overflow or stack full if you like, right? Whatever message you want to print there. That completes the code for the push function. Now we'll write the code for the pop function. And again, the parameters are char star from, char star to, and int star dist. Just check that we've put in that star there. So just put that in, right? It's an integer pointer, as you can see. And within this function, we'll check if top of stack is greater than 0, which means there is something on the stack to pop, then TOS minus minus, right, and mem cpy. The source, or rather destination, will be from. The source will be now BT stack of TOS or at TOS dot from, right, and number of characters is strlen of BT stack, right, of or at TOS plus 1, right? Similarly, mem cpy, and this will be now 2 being the destination. The origin or the source will be BT stack of or at TOS dot 2, comma, strlen, this is the number of characters, of course, BT stack of or at TOS plus 1, right? And then star dist equal to BT stack of or at TOS dot dist, right? If this condition is not met, meaning there's nothing there on the stack or nothing left on the stack, so printf stack underflow \n. And that completes the code for the pop function. So now that we've completed the code for all functions, 6 of them, right, we can now go ahead and build this, see if we have any errors. So here it says flight info has no member name skip. Yes, that's because it is skip over. So we look for wherever we put skip. I think that would be here as well, where we set it to 1, and as well as where we checked for it. So this will be dot skip over and again dot skip over, right? So let's build this again. F undeclared, this should be not F, it should be X, right? And X minus minus. Build again. Incompatible type for argument 1 of strlen. Oh, here we go. This should be dot from, right? +1. And this should be dot 2, right? So here we put in dot 2 +1. Now let's build. Right. So let's run this now and see the results. Put in New York and then Los Angeles. And we have the distance is 3000. So you see how the code worked, right? It's calling that find connect because we don't have a direct flight. And it finds New York to anywhere Chicago, takes the distance 1000. It's pushed that onto the stack. Then call find connect again, remember, using Chicago now as the origin. And then anywhere is Denver, and we've got the distance 1000. This, remember, is coming from the find direct function because there is a direct flight between Denver and Los Angeles. And therefore, we arrive at the distance 3000. Now, what you can do as well is in the root function, you could have another printf statement here, printf %s2, okay, and then comma bt stack of x dot from, okay. Let's build it first and then let's run it. So we say New York to Los Angeles, and you get this printed out. New York to Chicago to Denver to Los Angeles. That's the purpose of having that printf statement. Of course, you need to put some space in between there. So here you could put a space just to make it clearer on screen. Build and run again. And try that again. New York to Los Angeles. And there we are. So you get the entire route, right? So I hope this is clear. You can play around with this program. Now moving on. Now let's analyze the solution path we took, right? So here we have our origin and the same tree we saw earlier, the direct flights and then routes to different places, including, of course, to Los Angeles. And the solution path we found using depth first was this one, New York to Chicago, Chicago to Denver, Denver to Los Angeles. Now, of course, we wouldn't have found this directly. As you saw in the code, we've used recursion. So what we've done first is we've looked at flights from New York to any other place, and then from any other place to the destination. And that's how we've arrived at this solution path. Now let's analyze the depth first search technique. In our case, the good was that we found a good solution on the first try with no backtracking. The bad was, of course, that we would have had to traverse nearly all nodes to arrive at this optimal solution. Now remember, the term optimal is not really the best solution. It's optimal in terms of this search technique. And so the conclusion for the depth first search technique is that performance will be really poor if we had a long branch or a long subtree and we didn't find the goal or the solution at the end of it, because we'd have to backtrack and then look for another path. And this would result, of course, in a considerable waste of time. This concludes our discussion on the depth first search technique. As to the comparisons between all the different techniques, we'll do that after finishing our discussions on all the techniques, right? So this ends our session for today. In the next session, we'll talk about the breadth first search technique. Till then, take care, stay safe. Bye.